Well, it looks like I only had one slide left in this presentation, so this will be a short video, but maybe it'll give us a chance to recap the whole limit thing, which might prove helpful. Okay? So, indeterminate forms are the forms resulting from direct substitution of the limit value into the fractional expression, okay, which results in a 0 over 0. You will learn other indeterminate forms in calculus. For right now, we're only concerned about the indeterminate form resulting in 0 over 0. This is the one where you're dealing with a complex fraction, okay? So the long and short of it is to simplify the fraction, okay, algebraically, so that you can then do the direct substitution and evaluate the limit, okay? So that's what happens here, okay? Obviously, we're going to ask you to take the limit at the value for which the denominator is undefined, okay? And again, just because it's undefined does not mean the limit does not exist, okay? And the thing here, though, is if we put in 0 in the numerator as well as the denominator, we already said in the denominator we have 0. In the numerator, replacing 0, we got a half minus a half, which is 0. So we have a 0 over 0 indeterminate form. That's not a bad thing. Again, an indeterminate form is simply an indication that another method of attack has to be taken in evaluating the limit, okay? So the first indeterminate form we were up against, okay, said try factoring the expression. That's the easiest. Just make sure you know how to factor. The other method of the indeterminate form was the one where we had basically radical expressions, which we have to rationalize by multiplying by the conjugate over itself. And now this other form of indeterminate form which we're examining is the complex fraction form, okay, which simply says complex fraction is a fraction within a fraction. So therefore, the numerator is a fraction and the denominator is in the fraction, okay? The denominator is a fraction, all right? So that being the case, let's see we just simplify this algebraically. Okay, we determine the common denominator, which is 2 times the quantity x plus 2, 2 times the quantity x plus 2. So if we determine that is the common denominator, we're going to multiply by that common denominator over itself. Okay, again, here you are multiplying by 1. It's just that it's in this form, okay, of 2 times x plus 2 over itself. Okay, that'll distribute over your terms, as you can see, going from this step to the next, okay? Simplifying, okay, we'll eliminate the 2's. Then you'll be able to cancel the common factor of x. At that stage, you can do a direct substitution to evaluate the limit, and you're done, okay? So, going back and just kind of recapping everything, okay? The limit is, okay, a process by which you're asking for a particular function what happens as the x value closes in on a certain value. As x approaches a certain value, what is the function moving to, which is asking what is the y value, okay? You can look at that from an analytical standpoint. You can look at that from this table standpoint, tabular standpoint. Again, this right here is emphasizing the fact that you don't know what the limit is unless you determine both the left and the right hand side behavior. Okay, move at it, closing in very close to that value in question from value slightly greater, that's approaching it from the right, or the end value slightly less, which is approaching it from the left. If they agree to the same value, bingo, you got the limit, okay? If they don't agree, then the limit does not exist, as was the case here with our greatest integer function, okay? So in order to evaluate the limit, you have to look at it from both the left and the right-hand side, okay? Here, in most cases, you're always going to be asked the limit at some point of interest. The point of interest here is with x equals 0. Our understanding of the graph says there's an asymptote there. okay? Our understanding of the graph says on one side, on the positive side, it rises towards positive infinity. Well, that in fact is the limit. On the left side, it's falling towards negative infinity. Is it coming to the same value from both the left and the right? No. That implies the limit at that value does not exist. Here, owing to the asymptotic behavior of this function, and it's being squared, okay? Yes, we still have an asymptote at 1, but the left and the right side both crunch in on positive infinity. Therefore, the limit does exist and is infinity, okay? The piecewise graph, obviously, you're going to be asked for the limit at the points where we separate from one piece to another, which is at 0 in this and at 2. We separate. There's our, so that's in most every case, that's when you're going to be asked for the limit, okay? And again, if it doesn't agree, okay, here the limit approaches 0. From the left side, we go to 1. From the right side, we go to 0. Limit does not exist. Here at x, limit as x approaches 2. From the left side, we're going to -2. From the right side, we're going to -2. Even though the function at 2 is actually 0, that doesn't matter. The operative word is approaching from left and right. Approaching from left, approaching from right. Hit the same value, the limit exists. Otherwise, the limit does not exist, okay? There's an explanation behind that. We don't always have to check two-sided limits, okay? If the function, as is the case here, is, okay, not defined for anything less than 2, then it makes no sense to ask for what is the limit as x approaches 2 from the left, because it doesn't exist. But that does not preclude that the limit as x approaches 2 does not exist, because it only makes sense to look at it from the right side. The left side isn't even worth mentioning. And of course, hopefully you have an intuitive understanding of that, which does not leave you questioning why we have to do that. Same thing with going towards infinity. We're not going to come from one side of infinity and then the other side. It just doesn't exist. Speaking of graphs, speaking of limits going towards infinity, ask about the end behavior of the function. The end behavior of the function. The more you understand your function, the better you can answer the question, okay? The better you can answer the limit question, as we see here, okay? All these you should review and should know. Now, some might ask, well, what if I don't know what's happening at the ends of the function? Very good. To that extent, there will be in calculus, okay, a tactical approach that you will use, okay, to determine the limit as x goes to infinity. For our purposes right now, we're only concerned about functions we know something about. So for anything we're going to do at this point in time, the limit, asking the limit as x goes to infinity is simply asking for the end behavior of the function. The end behavior of the function. And of course, when we talked for the first time about the end behavior of the function, I introduced you to this notation, okay? So therefore, you should not feel uncomfortable with it at this stage, okay? All right? And lastly, in review, okay, we talked about some tactical approaches to solving for limits, okay? Not infinite limits, but limits going towards definitive values, okay? First order business, substitution. If you evaluate it with a substituted value and you get a number, that number is the limit, provided you did your calculations right, of course, okay? If you have a fractional expression, okay, and the fractional expression upon substitution reveals a 0 over 0, that's not a bad thing. That's the indeterminate form, which means further action must be taken. Further action must be taken. The first order of business you probably want to try is factoring. Factoring, okay? so that hopefully you can cancel out a common factor between the top and the bottom, allowing you to therefore evaluate the remaining expression by simple substitution. Okay? Rationalizing. Rationalizing always implies something that's done with a radical. Okay? Hence enters the word radical, rationalizing. It also introduces us or reminds us of something called the conjugate. The conjugate, which is, okay, two expressions which can be put into the form A plus B, A minus B. The conjugate of A plus B, A minus B. The conjugate of A minus B, A plus B. When you have expressions of that form, you multiply by the conjugate over itself. That's multiplied by 1, which has no impact except changing the form, allowing us to evaluate by substitution the asked for limit, okay? And then further, if this indeterminate form arises, which again is the first order business you get from simple substitution, you get 0 over 0, and it's something of this sort where it's a complex fraction. Do the algebra, simplify the fraction, then go back and evaluate the limit by simple substitution, okay? This is by no means all the tactical approaches you take for limits, but they're the ones that we're going to hold you responsible for until you get to calculus next year. There you have it, all about limits.